So we'll start with the phase rule, where we started with, okay. And the rule says basically the degrees of freedom or the independent variables we need, okay. That is C minus B plus 2. Okay. Now before we start, yesterday probably I wrote this thing, P1 by P, right? So that is pressure. So pressure to partial pressure, this should be mole fraction. I probably wrote it as a partial pressure. Okay. But that is mole fraction in the paper. Okay. Which means x1 and y1 are different. Okay. And it makes sense because if you remember what was the pressure relationship, there was a relation between x1 and P, y1, sorry. So like I could have written y1 as x1 P star divided by P star So, suppose actually I have P1 and P2 are equal, okay, which means the vapor pressure of the pure liquids 1 and 2 are equal. Then what I have? Y1 and x1 are same. Okay. Until and unless that situation is fulfilled, meaning the two liquids which are both volatile, but they are not volatile to the same extent, then actually x1 and y1 are different. Okay. Which means the mole fraction of a component in the liquid phase is very different from the mole fraction in the vapor phase. That's it. Okay. So that's why you are seeing a difference. Now again, long story short, what we started is that we talked about a phase diagram, which is like our standard way of looking at phase diagrams is something like this, right? Pressure, temperature, we always show for a single component, right? But what we drew yesterday, something like pressure versus mole fraction of a component, exhale. So that is also phase diagram. Okay, phase diagram of what? It is basically pressure versus mole fraction phase diagram. Clear? At a fixed temperature. Clear? Again, for a two component system, what you will have? We will have 2. Okay. 2 and 2, 4. It is basically 4 minus 2, 4 minus P. Okay. Now it will depend what is your P. Okay. So let me write it in this way. So we are talking about two components, 1 and 2. Okay. So C is basically 2. Right. So overall, my F should be basically 4 minus P, right? Now remember that I am also making another constant. What is the constant? Fixed temperature. Okay. So if I have a fixed temperature, okay, so then F will be 1 less, right? It will be basically 3 minus P. Clear? Okay. Now the question is, where we are looking at? And we showed that, okay fine, if I just plot it as a function of x1, I'll have something if the solution behaves ideally, right? But this I talked about liquid, right? Now suppose I am somewhere here in this region. So that's a liquid region because it's a high pressure region, right? In high pressure region, if it is in the liquid region, then actually what is P? Number of phases. It is just 1, right? If P is 1, then I have basically 2, right? Degrees of freedom. What are these 2 degrees of freedom? Pressure and mole fraction. Clear? Okay. So like for any pressure, I will have many mole fraction present, which are allowed. Okay. For this phase to be stable. Okay. Moment I am on this line. Now what is happening? Line means actually it is separating liquid and vapor. So actually 2 phases are coexisting. This is exactly identical to the earlier diagram line. Okay, but it's slightly different. That was a pressure temperature line. This is basically pressure composition line for a fixed temperature. But again, you need lines because the lines are basically separating the phases. Okay. Now on this line, what is now P? P means basically the number of phases. This is the actual pressure. Okay, we should write it as small p. So what is the number of phases? This is 2, right? So it will be basically 3 minus 2, which is 1. And it makes sense because if you fix the pressure, there is only one thing variable because this is all lying on the line. Clear? Okay. So here, basically in this region I have F is equal to 2. In this region I have F is equal to 1. Okay. Some textbooks actually write it as F prime in the sense that actually F is 3 but we fix temperature. Okay, here F is actually 2 but we fix temperature, so it is 1. Okay, if you read Atkins, I think he has used F prime notation, whatever it is. Okay, but whatever it is, so like on this line F is equal to 1. Okay, but for the bulk phases, I'll always have basically F equal to 2. Okay, and then we said that I could actually plot the composition with respect to Y1 also, which is the mole fraction of component 1 in the vapor phase. Okay, but that is very different curve, something like this. Okay, now someone was asking whether it should be below or above. I think you were asking. Okay, so in this case it will be below, will come where it will be above. Okay, because think about it, like this corresponds to vapor, right? Vapor mole fraction. So the idea is that vapor is a stable phase always at a low pressure region. Clear? Always. Okay. Now, yeah. So that's why the liquid line always lies above. Okay, but we'll see that for a different condition it will be reversed. Okay. Now the question was basically then I was telling you that can we actually write this thing instead of not x1 and y1 but say overall mole fraction. Okay. And again, there are different notations. Some textbooks write it as x1. Let me just use something like z1. So z basically tells you the mole fraction of 1. It can be equal to x1 if it is in liquid phase. It is equal to y1 if it is in the vapor phase. Okay, that's it. Now the question is fine. Suppose I start from here. Okay, let me actually draw it. Slightly bigger word. The same curve I'm going to just redraw it. So what I have is this, and I have this is for the liquid, okay, and this is for the vapor, okay, or gas. Now here, this is a bulk phase, F equal to 2. This is also a bulk phase, F equal to 2, but in between, basically, I'll have F equal to 1 because liquid and vapor are in equilibrium. Okay. From this line to this line, that entire region. Clear? Okay. Now, just take an like example. Okay. Suppose we start from here. Okay. Say I start from gas. Okay. And what I'm doing, I'm actually increasing the pressure. At constant temperature, of course, temperature is fixed. Okay. Now what will happen? I'll reach a point, like suppose this is a some composition, right, which is basically Y1. Okay, because I am starting from the vapor composition. Okay. And then I am increasing the pressure. Okay. What will happen? At some pressure, okay, I will see that now the vapor basically starts forming the liquid. Okay, but until and unless I reach this pressure, for this composition, okay, vapor is the most stable form. Clear? Okay, and then I'm reducing the pressure. Okay, and suppose I reduce it further somewhere here. Now the question is, what is the composition here? Now this is something like, you can think like the total composition, which was basically identical to Y1, but here it doesn't make sense because where it will lie? Okay, it is in equilibrium with vapor and liquid. Okay. So then we said that okay, fine. Let us draw a line. Okay. For that pressure, okay. What we'll find if we maintain that pressure and that constant temperature, and if we had started from a composition of the vapor, which is Y1 here, okay, what will happen? It will basically now give you, it will basically fractionate, okay, between liquid and the vapor, because it is in equilibrium, okay. And that point, basically the liquid has this much mole fraction and the vapor has basically this much mole fraction. Clear? You could also think the other process, like if I start with a liquid phase point and then if I go down, okay, the same thing happens. So the lines are again basically the point where actually we are starting the equilibrium. Okay. Now these lines have a typical name. Okay. Just try to. Yeah. So this horizontal line we call as tie line. So it's basically for a fixed pressure. Okay. For a fixed composition, we call it as a. Anyone knows what is that thing? It's called isoplate. CHM202 just covered it. No. 202 just covered. Covered or not? Covered, right? Yeah. So this is basically isoplate. Okay. Now the question is, okay, fine. Now what will be, okay, the corresponding thing if I suppose change the temperature? Okay, that will come quickly. But before going to that, let us just try to make a relation, okay, between say this quantity, which is Z1 means overall composition, okay, and what are the quantities this Y1 and X1, okay, just from geometry. Okay. So what I'm saying here is that if I start from a fixed composition, okay, which means again I am on an isoplate. Okay, fixed composition means vertical line. Okay. Now think about it. If I'm increasing increasing the pressure, okay, or decreasing the pressure, what is happening is that I reach a line, okay, basically either the top line or the bottom line, and then I enter a region where actually that line will not be there because it should be either vapor or the liquid. Okay, so it will basically have X1, Y1 kind of composition. Clear? Okay. So how to basically think about that? Meaning I started from a particular composition Z1 that is fixed. Okay, but Z1 you can think is now split into X1 and Y1. Okay. So how do I get a relationship? Now the relationship is very easy. Basically, it's coming from geometry. You have a middle point here. Okay, this is X1, this is basically Y1, and this is Z1. Okay, and that sometimes is known as a lever rule. Okay, so let me just quickly show you how the lever rule is, like how you can actually hear the lever rule. It's just two-line rule. Okay, so suppose the total number of moles. Okay. In alpha and beta phase, or something like in alpha and in beta, okay, and the overall amount of one, okay, which is N1. What will be N1? So N is the total number of moles, okay, not 1 and 2. Like suppose I have water, benzene and water, or say water and phenol. Okay, both are volatile. Now this means actually total number of moles, okay, of water and total number of moles in the alpha phase, okay, which is the liquid phase, and which is in the beta phase. And if I ask you what is N1, okay, N1 means this total number of moles multiplied by the mole fraction. Okay, mole fraction of what? In the overall mole fraction, right? Meaning Z1. Clear? So Z1 means actually overall composition. What was your mole fraction? Okay. Now Z1 again has a meaning when I am either in this phase or in this phase. But here the composition cannot be Z1. It will just split. So here actually Z1 is equal to Y1. Here Z1 is equal to X1. But here the Z1 will basically be split into X1 and Y1. Clear? Okay. So by definition, the mole fraction of 1 in both alpha and beta phase, okay, should be the total number of moles times what you started with. Suppose that is Z1. Clear? Okay. Alright. So then I can write actually NZ1, okay, which is nothing but the mole fraction of 1. Okay. So what that will be? That will be nothing but equal to the alpha phase mole times the alpha phase mole fraction of 1. What it will give you? The number of moles of 1 in the alpha phase. Clear? It's just a notation thing. It's just two-line proof. Okay. So what I'm saying here is that, okay, let me just write another line. So what is N1? N1 is the total number of moles of 1. Fine. What is N1? N1 is that, okay, let us calculate the total moles, which is N1 plus N2. Okay, N is nothing but equal to N1 plus N2 in the all the phases, alpha, beta, whatever. Okay, everything together. Okay, is N. Now I take this N, multiplied by the mole fraction, overall mole fraction of 1. That is basically you will give me N1. Okay. Now this N1 is in alpha phase as well as in beta phase. Right? Now how do you calculate what is in alpha phase? You calculate the total alpha phase multiplied by the mole fraction of 1 in the alpha phase. Now mole fraction of 1 in the alpha phase is x1. Okay, what about the beta phase? Basically the total number of moles in beta phase times the mole fraction of 1 in the beta phase, which is the vapor phase. So y1. Clear? Okay. So that is one equation, but then think about it. The same quantity, okay, I could have written as like it's the same interpretation. Like think about it. Like I have one component. Okay, I'm asking what is the. Let's just actually take something like, let's say I'm talking about only water. Okay, in water phenol mixture. Okay, what is the number amount of water? It is basically water for phenol together times the water's mole fraction. Okay, overall water's mole fraction. Okay, which is basically I have to take water per phenol in alpha plus water per phenol in the beta. The total thing. Okay, so that I have written in the clever. I have written in the alpha phase. Look at it in the alpha phase and look at it in the beta phase. Okay, when I am taking in the alpha phase, I am writing x1. When I am writing in the beta phase, I am writing y1. Okay, let me just write the notation. Yeah. Now, think about it. If Z1 is the overall composition, okay, just look at it, NZ1. Okay. Now, what is N? N means total thing. Okay, but that I could have written as N alpha. Like, let me just write it as NZ1 is also N alpha plus N beta. Okay. Into Z1, that also I can write. Okay. Which I can just write it as N alpha Z1 plus N beta Z1. Okay. Now these two equations are identical. Just equate it. Okay. If I equate it, then I'll have something like, just follow this thing. Okay. I have N alpha Z1 plus N beta Z1 is equal to N alpha X1 plus N beta Y1. Okay. So I'll just collect terms. Okay. And write it as N alpha. Okay. It will be basically, if I take the left hand side, X1 minus Z1. Okay. And then on right hand side I should have N beta the other way. Z1 minus Y1. Clear? Okay. Now what is your X1, Z1, Y1? So this was our Z1. Okay. This is, here actually Z1 is equivalent to Y1. In this case Z1 is equivalent to X1. Here I have a problem. Okay, so this is X1 and what is this is basically y1. Clear? And this is z1. Okay. So what is your x1 minus z1? x1 minus z1 will be which one? Or I could have written it as a z1 minus x1. I mean, that doesn't matter. Basically, there will be a minus sign. Okay. So x1 minus z1 means what? Negative of this thing, right? And z1 minus y1 will be negative of this. So these two lengths are basically those two quantities. Okay. Or study carefully. This is x1. This is y1. Okay. And the middle point was 0. Okay. So what I'm saying is that this thing and this thing are basically this and this. Just the length. Okay. So what I got is that basically n1 into length of this, okay, n alpha into length of this is basically n beta into length of this. Okay. So what I got ultimately, you are getting a relation of n alpha and n beta. What are n alpha and n beta? How the total moles are in the alpha phase and beta phase. What is total mole? What is water plus phenol in the alpha phase? What is water plus phenol in the beta phase? Okay. And how they fraction it? We see that basically n alpha plus n beta is nothing but this length, which I can call it as a, say, L2 and L1. So this just goes like this. Okay. So this comes from simple geometry, and this is known as basically lever rule. Okay. So the lever rule basically tells you if I have a phase diagram, okay, in the pressure composition plot, okay, in the region where I have the two phases coexisting, okay, there I can always get a relation of the relative ratio, okay, of how much is in the alpha phase, how much is in the beta phase, just by looking at the diagram. Okay. For a fixed like composition. Okay, because everything I started from a fixed composition, then actually we'll get a two lengths. Clear? Alright. Now let us not think too much about the lever rule. Let us just try to understand what is the basically the physics of it. Okay. When instead of pressure, I'll change it to temperature. Now why that is important? Think about it. I have a mixture. Okay. And suppose I am boiling it. Now the question is, I have two volatile compounds, right? Now physically what is happening if I keep on increasing the temperature? Okay. Now the compound which is more volatile, that will come out, of course, right? And then once it comes out, I'll have an interesting situation. What is left? Okay, suppose one is more volatile than two, so one comes out at a more rate, right? But what is left? That composition or the solution will be now enriched in two, right? So I'll have an interesting dynamics as time progresses. Okay, what is it? So instead of a pressure composition diagram, I should actually now switch to a temperature composition diagram. Okay. However, the degrees of freedom will be still the same. Why? Because in that case I fix the temperature. Here I am fixing the pressure. That's it. Okay. But the diagrams will look different. How different? First of all, see, for a higher pressure, liquid is more stable than vapor. But if this is temperature, actually liquid is more stable in a lower temperature. So the line for the liquid will be lower, line for the vapor will be at higher. Okay. Also, you can show it, which I am not showing right now. This won't be actually a straight line for liquid, it will be a curved line. Because you are now comparing, basically you can actually use PV equal to nRT and then cast the problem into basically a temperature composition kind of problem. Okay. But the pressure is kept fixed. Clear? Okay. Because usually when you do boiling, okay, we are doing boiling at 1 atmospheric pressure. Okay, we are not changing the pressure. Clear? Okay. So a natural thing to consider is that keep the pressure fixed, but look at the phase diagram, okay, as a mole fraction versus temperature plot. So all we are going to do, and we'll just discuss it very qualitatively. Okay. So instead of constant temperature, I will have a constant pressure here. Okay. We need to use two different conventions. Okay, fine. Now, so what I'm telling you that both of the curves in this case will be nonlinear. You can show it. Okay. Now, again, the lower curve in this case will be the liquid curve. Okay, because the liquid is more stable at the lower temperature. So suppose the curve is something like this. Okay. And then also I have a vapor curve, which is something like this. Okay. So this is a phase diagram. Okay. For a two-component system, say let's say two solvents, it's a binary mixture. Okay. And where I'm plotting it as a function of temperature and mole fraction of one of the components. Clear? Okay. Now let us see what will happen if I start boiling. Okay. Now suppose here I have what? I have liquid here, right? And I have vapor here. Again, degrees of freedom is 2 here, degrees of freedom is 2 here, and degrees of freedom is 1 here. Okay. And suppose I am somewhere here, meaning I am starting with a composition which is something here. Okay. And I am increasing the temperature. So once I increase the temperature, what will happen? So up to this point, okay, the liquid is stable, and at this point, basically the boiling starts. Okay, because the equilibrium is established. Once the equilibrium is established, I see that then it will fractionate for a fixed temperature. Something like suppose you are boiling water. Okay, you are basically heating it up, rising the temperature. Once 100 degrees centigrade is reached, it starts boiling. Okay, something like that. Okay, but it's not pure water now. It is water plus something. So the boiling point will be a little bit changed. We know that because there is a freezing point, depression, elevation of boiling point. All these things will happen, right? So it's not actually 100 degrees, something else. Okay, but let us not discuss what is the something else. So some temperature. Okay, it starts. Now when it starts, it means at that point when it will reach. Okay, then there is an equilibrium, right, for this temperature. Clear? Okay. So then I'll have basically vapor, which is a composition of this, and liquid, which is a composition of this. This is a very interesting thing. Meaning what I'm saying here, I had something like say water and phenol. Suppose I have 30% water. Okay. And say 70% phenol. Suppose. Okay. And then all of a sudden I am increasing the temperature. And the boiling point for the phenol water mixture is reached. Okay. Once it is reached, suppose one is water. Okay. I see the water vapor. Okay. Actually comes out quickly. Okay. And then that vapor now is enriched in the mole fraction of 1. Okay. So for the higher volume, okay, this will happen. Because all these curves are drawn in such a way that PS star is more than PB star. Okay. Because if you plot it, if you just take an like any plotting software, okay, you have this y1 versus this thing, right? I showed you. So now that curvature will depend on whether the PA and PB, what is the relative ratio of P and P. Okay, the idea, the way we wrote it is basically P star is more than PB star. Okay.